Two teams of scientists studied the exact same fault in Northern California. One team says the worst it can produce is a magnitude 6.5. The other says 7.2, with almost 19 feet of ground moving sideways in a single event. 11 years apart, and nobody has settled which one is right, because this fault runs through terrain so remote you can't even put instruments on it. Then, this week, it did something that lands right in the one section neither model actually covers. Two earthquakes, 59 seconds apart, in a gap in the science itself. By the end of this video, you'll know exactly what the evidence is now pointing toward, and why that's not the reassuring answer everyone was hoping for. Let's start with the sequence itself. On Wednesday afternoon at just after 3:20 Pacific Time, the ground moved about 19 miles northwest of a small town in Mendocino County called Covelo. The U.S. Geological Survey logged it as a magnitude 4.1 at a depth of roughly 5 miles. On its own, that's not much of a story. Northern California produces earthquakes this size regularly, and this one hit country so empty almost nobody was close enough to feel it. 59 seconds later, it happened again. And this one was bigger, a magnitude 4.5, same general location, but shallower, at less than 3 miles down. A seismologist reviewed this one by hand rather than trusting the automated system, which tells you it was taken seriously from the start. These two weren't the beginning either. A regional earthquake monitoring group had already flagged a magnitude 4.0 the evening before, in the same spot. So the full picture is 3 moderate earthquakes across about 22 hours, in a stretch of land with no towns, almost no roads, and very little seismic equipment watching it. Despite that emptiness, the shaking traveled far. People felt the largest quake from the Sacramento Valley all the way out to the Humboldt coast, roughly 200 miles. Nobody was hurt. Nothing was damaged. But 200 miles of felt shaking from a magnitude 4.5 isn't typical, and the reason comes down to depth. At under 3 miles down, that earthquake was unusually shallow, which concentrates energy near the surface instead of letting it spread out through miles of rock. It also means a much larger earthquake on this same patch of ground, at this same depth, would hit far harder than its magnitude alone suggests. This all happened on a structure called the Bartlett Springs Fault Zone. If you've never heard of it, that's not an accident. It's one of the least discussed major faults in California. It's actually one of 3 parallel branches of the San Andreas system running north of San Francisco Bay. The San Andreas itself hugs the coastline. The Macama Fault runs through the middle. Bartlett Springs runs farthest inland, quietly absorbing a share of the plate motion that the San Andreas doesn't carry. And out of the 3, it's by far the least studied. There's no earthquake anywhere in the historical record that scientists can confidently pin on it. Even something as basic as its length is disputed. Depending on which study you read, it's 170 kilometers, or 120, or as short as 85. That's not a rounding error. That's the first clue about how little solid ground there is here, scientifically speaking. The fault doesn't stand alone, either. It runs southeast, connects into the Hunting Creek Fault near Clear Lake, which links into the Berryessa Fault, which becomes the northern end of the Green Valley Fault. Follow that chain far enough, and you're standing in the East Bay, one of the most densely populated regions in the entire country. This isn't some isolated crack in the forest. It's the northern end of a structure that eventually threads through millions of people. Then there's the slip rate, how fast the two sides of the fault are actually moving past each other, and this is where the published science stops agreeing with itself entirely. GPS-based measurements put it somewhere between 4 and 8 millimeters a year. One detailed modeling study from 2014 lands on 7.5. A separate assessment from a well-known seismologist puts the long-term rate closer to 1 or 2. That's nearly a 9-fold range on the same number. And when scientists can't agree on how fast a fault is loading, they can't agree on how much energy is building up inside it, which means nobody can really balance its earthquake budget. That uncertainty is about to become the whole point of this story. Here's what makes Bartlett Springs genuinely unusual. 2 respected research teams each built their own model of how this fault behaves underground, and their conclusions don't just differ slightly. They point to two completely different worst-case earthquakes. The first model, published in 2014, argues the fault is locked from the surface down to about 10 kilometers. Locked means stuck. The two sides aren't sliding past each other at all, they're jammed, quietly building up strain that eventually has to release all at once. When another team ran the numbers on that scenario the following year, they calculated a maximum possible earthquake of magnitude 7 to 7.2, with close to 19 feet of horizontal slip in a single event. The second model, from a different team the same year, argues almost the opposite, that most of the fault below 5 kilometers is creeping, sliding continuously and quietly, a fraction of a millimeter at a time, instead of storing energy for one violent afternoon. If that's true, there's far less stored energy available, and the maximum earthquake drops to somewhere around magnitude 6.5 to 6.7. That gap matters more than it might sound. A magnitude 7.2 releases roughly 11 times the energy of a 6.5 and produces about 3.5 times as much ground movement. One of these outcomes is a serious regional earthquake. The other is a generational disaster for inland Northern California. And the entire disagreement comes down to one question: how much of this fault is essentially greased, and how deep does that grease go? Until recently, there was no good way to answer that, because the terrain makes it almost impossible to plant seismic instruments. In 2024, a research team took a different approach entirely. If you can't directly measure whether the fault is sliding, measure what it's made of instead, and work out from the rock itself where slippage is likely. The rock they were looking for is called serpentinite, a soft, greenish, chemically altered rock that's known to reduce friction wherever it shows up inside a fault zone. It's also strongly magnetic, which means you can map it from the air instead of hiking into terrain nobody can reach. So that's exactly what the team did, flying magnetic and gravity surveys across more than 100 kilometers of the fault, funded in part by the utility company that operates a dam sitting almost directly on top of it. What they found across most of the fault was more of this slippery rock at depth than anyone expected, which pointed toward the creeping, lower magnitude model being closer to correct. If the story stopped there, this would be reassuring news. It doesn't stop there. Two details in that same study change the picture entirely. First, the pattern breaks down at the northern end of the fault. In the researchers' own words, the slippery rock up there is either confined to the uppermost kilometer, or sits off to the side of the fault rather than inside it, meaning everything below that shallow layer may be ungreased and capable of locking up. The argument for a lower magnitude fault applies to the central and southern sections. The northern end doesn't clearly qualify. Second, and this is the detail that matters most, the study states flatly that it doesn't extend its analysis north of a specific point called Round Valley. That's the edge of the map. The best modern understanding of how slippery this fault is has a hard boundary, and past it, nobody has done the work. Now place this week's earthquakes on that same map. They struck roughly 19 miles north-northwest of Covelo, at or beyond that same boundary, sitting in the one section of the fault the newest science doesn't cover. That matters because these kinds of boundaries, where creeping rock meets potentially locked rock, are exactly where earthquake ruptures tend to start, and exactly where they tend to stop. There's also a structural complication right at that location. The fault's geometry shifts there in a way that creates a compressional bend, a spot where the rock gets squeezed rather than sliding freely. Squeezed spots concentrate stress. And that's precisely where this week's earthquakes happened. There's a reasonable counterargument, and it deserves mentioning. Creeping faults aren't silent. They regularly produce small earthquakes as tougher patches of rock resist and eventually give way. That's expected, normal behavior. But that framework typically predicts earthquakes below magnitude 3. What happened this week was a 4.0, a 4.1, and a 4.5, a full magnitude unit or more above the expected background noise. Because the scale is logarithmic, that's not a small gap. It's tens to hundreds of times more energy per event than the normal creep explanation comfortably accounts for. The sequence shape adds to the picture too. In a typical mainshock-aftershock sequence, the biggest earthquake comes first and everything after it fades. This week did the opposite. Smallest first, biggest last. which is the signature of a swarm, often driven by fluid movement underground or slow, cascading slip rather than one patch simply letting go. If Bartlett Springs has never produced a large earthquake in recorded history, why worry at all? The answer comes from a trench, not a seismograph. Researchers digging across the fault in the 1980s found evidence of at least 3 prehistoric earthquakes, the most recent occurring somewhere between roughly 300 and 1,000 years ago. To leave that kind of mark in the ground, a rupture typically needs to be larger than magnitude 7. So this fault has broken big before. It simply hasn't done it during the roughly 170 years California has kept written seismic records. Hasn't broken recently is accurate. Has never broken is false. And creep doesn't mean safety either. 6 weeks before this sequence, the neighboring Makama fault, a fault known to creep continuously and measurably, produced a magnitude 5.6 earthquake that cracked buildings and knocked out power to 10,000 homes. Creeping faults can still hurt people. So here's what actually matters going forward, and it isn't the magnitude of what already happened. A 4.5 released only a tiny fraction of what this fault is capable of storing. What matters is location. If future activity stays clustered right where it is, that's most likely a single stuck patch letting go, and nothing more. But if a new cluster appears further northwest, migrating deeper into that unmapped gap near Round Valley, that's a meaningfully different signal. Activity spreading into exactly the section of fault nobody has been able to study. The other thing worth watching is whether anyone extends that aerial mapping north of the current boundary. Right now, the honest answer about the northern half of this fault isn't that it's dangerous, and it isn't that it's safe. It's that almost nobody has looked, because almost nobody lives there. That, more than any single earthquake this week, is the real story. A fault capable of producing a magnitude 7, running toward one of the most populated parts of the state, with a measurement gap sitting exactly where this week's earthquakes happened.